Okay, scholars, so we're going to go ahead and get started with Unit 6. Unit 6 is chemical kinetics. That word kinetics coming from the root word kine, meaning motion or movement. Chemical kinetics is all about the rates at which reactions occur, how quickly they occur, the speed with which a reaction occurs. So you know that we have a way of discovering whether or not a process is possible, whether or not it's favorable at a certain temperature. We call that thermodynamic favorability, and of course that's our delta G, our Gibbs free energy function. If delta G is negative, we know that the process is favorable at that temperature. That means that the entropy of the universe is increasing in adherence to the second law of thermodynamics. But let me remind you that just because a process is thermodynamically favorable, just because the delta G for a process is negative, does not mean that the process will occur or that it will occur quickly. So if we want to know how quickly a process will proceed, we need to study kinetics, the rate at which a reaction occurs, the rate of chemical processes. We define that term rate of reaction as the speed of the reaction, defined as the change in concentration of a reactant or product per unit time. So how is the concentration? Remember, concentration is typically measured in moles per liter. So how is the amount measured in concentration? How is the amount of a reactant or product changing as time goes on? If those amounts change very quickly, if our reactants get consumed very quickly and our products get produced very quickly, if we have a large change in concentration per time, that means our reaction is happening fast, right? Let's talk about graphs. Let's consider this simple reaction, substance A being converted to substance B through a chemical process. We can create a graph of the number of molecules, which would be proportional to the concentration of that substance as time goes on versus time. That's what this graph here is doing. So here you can see in purple, this would be the number of molecules or the concentration of substance A as time goes on. Obviously, it's going to be decreasing because substance A is getting consumed. Substance B is getting produced, so its number of molecules will be increasing as time goes on. And here you can see, according to this graph, 60 seconds later, all of substance A has been chemically converted to substance B in this chemical reaction. So how do we define the rate? By looking at a graph like this. If you are given a concentration or amount versus time graph, the rate of the reaction is just the slope of that curve. Because if you take the slope of this, slope is rise over run, y change over x change, then you're going to get number of molecules over time, change in concentration per time. That's how we just defined rate. So we could write an equation for that. Let me talk to you about these equations that are written right here. Delta, of course, means change in. Whenever you see something in brackets, that means concentration. So we're talking about the change in concentration of substance A over time. That is how we would define the rate. That's synonymous with the slope of this curve. Because in this chemical process, for every one molecule of A that gets consumed, I produce one molecule of B. The rates are related like this. For every one molecule of A that gets consumed, that's what that negative sign is there, the slope of this purple line is negative, right? It's decreasing as time goes on. For every one molecule of A that gets consumed per second, I'm producing one molecule of B per second. Let's look at this graph. These graphs are curved lines. You should know that mathematically speaking, a curved line is defined by the fact that it has a changing slope. So whenever you are dealing with slopes of a curve, I encourage you to look at the graph in segments and think about what the slope is like over some small segment of the graph. Here you can see that the slope of this purple line starts as a large negative value. It's declining quite rapidly. But then as we go on, the slopes kind of shallow out. This curve gets flatter and flatter. What does that mean about our rate as time goes on? That means that the rate itself is changing. In other words, this reaction is slowing down as time goes on. It starts quite quickly. A is declining rapidly, B is growing rapidly, because at the beginning these curves have steep slopes. But then as time goes on, the slopes get shallower and shallower. My change per time gets smaller and smaller. So here we would say that the reaction is slowing down as time goes on. This is important. It makes conceptual sense that the reaction would slow down as time goes on, because as the reaction proceeds, there's just less stuff to react. It's going to turn out, this is incredibly important, that the rate of a chemical reaction typically depends on the concentration. The rate of a reaction depends on the concentration. I have this written on a slide later. But if the concentration, if the number of molecules of A that I have available to react is decreasing as time goes on, because as the reaction proceeds, A gets consumed, B gets produced, then it makes sense that my reaction is going to slow down, because I just have not as much A left over to react as time goes on. Okay, here is some time and concentration data for this chemical reaction right here. 2 moles of NO2 yield 2 moles of NO plus O2. You should recognize this as a decomposition reaction. I have one substance decomposing into 2 substances. And we can see that there is a concentration versus time data that's given to us. So if we study a graph of this, here you can see that NO2, that was our reactant, right? So its concentration is decreasing as time goes on. NO and O2, those are our products. So those concentrations are increasing as time goes on. And you can see that, just like the last example, as time goes on, the reaction slows down. The curve gets shallower and shallower. Remember, the slope of a concentration time graph is how rate is defined. This image is showing you how a slope of a curve could be calculated. For those of you who are familiar with mathematics, especially calculus, you'll be familiar with this concept. But if I want to figure out what the rate of change is, what the slope is at this point right here, what I can do is draw a tangent line. You all should know what a tangent line is. It's a line that touches a curve at only one point. A tangent line, and I can find the slope of that tangent line. And that's what this graph is showing, or that's what this image is showing right here. Slope is rise over run, so this tangent line has a fall of 0.0026 and a time change of 110 seconds based on the graph. So we could find the slope at each point by drawing a tangent line and finding the slope of that tangent line. And that's what this image is showing you all throughout here. Now, what's interesting to note is that it looks to me like the O2 concentration is rising more slowly than the NO concentration. And I want to discuss why that would make sense. Let's go back and look at what the reaction is. The reaction says that for every 2 molecules of NO2 that get consumed, 2 molecules of NO get produced, but only 1 molecule of O2 gets produced. So as time goes on, it makes sense that I'm going to be making less O2 just because of the stoichiometry of the thing. And if I'm making less O2, then of course O2 is going to be rising at about half the rate that NO rises. And that's exactly what we can see here. Here they're finding the slope of the tangent line is at 70 seconds. This tangent line rises only 0.0003 for my oxygen, but my NO line at that point in time rises 0.0006. It rises double that. We're going to talk later about how we can think through the way that rates are related to each other for different substances, but right now it makes pretty good sense that my NO would be growing at twice the rate of my O2, because once again the stoichiometry says that for every 1 molecule of O2 I make double the number of NO molecules. So right now you guys should understand these concentration time graphs. You should understand the idea that the slope of these graphs is the rate of the reaction from the perspective of a certain chemical. We could talk about the rate of consumption of NO2 or the rate of production of NO or the rate of production of O2. And you should understand that those rates at any given moment in time will be the slope of the tangent line drawn at that point. That's the slope of the curve. For your exams, you will not have to like find the slope of a tangent line, but it is an important idea for you to know conceptually. I don't want to talk about that. Okay, let's talk about rate laws. This is like the meat of this kinetics unit. First, I want to note that reactions are typically reversible. They can happen in a forward process or a reverse process. Excuse me, they typically happen both of those ways. But for this unit, we're just going to focus on the forward reaction. So this is very important. We're going to assume in this unit, next unit it's going to be different, but in this unit we're going to assume that reactions proceed from left to right, reactants get consumed, products get produced, just like we've always done. And we're going to define the rate in terms of the reactants. So we always have to define the rate from the perspective of something, from the perspective of some chemical. Remember, we just saw that rates are different for different chemicals. All three of these chemicals are involved in the same reaction, but you can see that O2 and NO have different rates. NO has twice the rate of production as O2, so we have got to define what chemical we are taking the perspective of when we calculate what the rate is. Typically, we're going to take the perspective of the reactants. Okay, we're going to learn how to write special equations called rate laws. A rate law is an equation which expresses the rate of reaction in terms of concentration and time. We have two different types of rate laws. I want to go over the first type with you today. Our two types of rate laws. If you've taken calculus, you can come talk to me, come talk to me later about how all this relates to calculus, but you'll recognize these terms from calculus. We have the differential rate law. Very important that you understand that a differential rate law is an equation that relates the rate of a reaction with the concentration of reactants. Listen, we have already discussed that as time goes on, the rate of a reaction typically changes because the rate depends on how much crap there is to react. If I'm decreasing the amount of A available to react, it makes sense that the reaction will proceed slower and slower and slower. Rates depend on, typically, not always, but they typically depend on the concentration of reactants available to react. An equation that relates those two variables, the rate of the reaction, the speed of the reaction, and the concentration, we call it a differential rate law. The other form of the rate law is the integrated rate law. It expresses how the concentration of reactants depend on time. How does the concentration change as time goes on? So please, please, please note how these two equations have different goals. They relate different variables. Rate versus concentration, concentration versus time. Today we're going to talk about the differential rate law. So once again, a differential rate law is an equation that expresses how the rate of the reaction depends on the concentration of reactants. It relates the rate to the concentration. So here is the pattern. This is the general form of the rate law. Your rate laws that you write will be different based on what your reaction actually is. But let's say that we have this reaction. Substance A plus substance B react to yield substance C plus substance D. What do you think I'm telling you with these little letters out in front? Yeah, those would be like the stoichiometric coefficients. For every 1 mole of A, I need 2 moles of B, etc., etc. So those little a, little b, little c, little d, those would be the mole ratios, the stoichiometric coefficients that you have in your actual chemical equation. Every rate law will take this general form. R, where R is the rate of the reaction, that will typically be in R is usually in units of molarity per second. Remember, it's concentration per time. Rate is how does the concentration change as time goes on. So molarity per second. What does molarity, capital M, mean? It's a measure of concentration. So we could rewrite that as moles per liter. That is also what molarity means. Moles per liter seconds, right? So moles per liter times seconds with liter seconds on the bottom there. Another way of writing that would be moles times liters to the negative first power times seconds to the negative first power. Remember, if you take anything to a negative power, it's 1 over that. So 1 over liters to the first power times 1 over seconds to the first power. You guys need to be familiar with these different ways of expressing units. Units of measure are going to be really important in these rate laws. So please take a moment to make sure this makes sense to you. Molarity per second is how we measure R, the rate of the reaction. Big R is the rate of the reaction. Molarity per second, concentration change per time change. Molarity is moles per liter. So we can say moles per liter seconds, where liter and seconds are both on the bottom. Or we can rewrite that as moles times liters to the negative first times seconds to the negative first. My little dumb asterisk here is my way of saying times, I guess. Okay, this rate law should make sense to you. We know that rates are tied to concentration. We've seen that in the graphs. We've talked about that several times. Rates typically depend on concentration. So that's exactly what this rate law shows. It shows that the rate somehow depends on the concentration of, again, we typically take the perspective of the reactants. So that's what the bracketed A and B are. That's the concentration of your reactants at any given time. So think about this, as time goes on, what is happening to the concentration of A and B? Well, they're getting consumed in a chemical reaction, aren't they? So they're going down. So what's going to happen to the rate? The rate is going to slow down. That's exactly what we said earlier. So the rate depends on the concentration of A and B. For a forward reaction, A and B reactants are getting consumed. Their concentration decreases, so as time goes on, the rate will decrease. That's exactly what we saw earlier. As time went on, the slope of the concentration time graph was dropping. Let me talk to you about all the other letters in this equation. K is something known as the rate constant. It's going to be a number, it's going to be a value, and it typically must be determined experimentally. That means that you have to do an experiment. Hopefully, we'll be able to get in the lab and do our own experiment to determine the rate law and the K value for a chemical reaction. It's got to be determined experimentally. It's a rate constant. You must know how to derive the units for K. The units for K will change depending on the rest of the equation. So you need to know that, and we'll talk about this later, that K is a rate constant. It has a value. It has specific units. You later will practice figuring out what those units are, okay? Now let's talk about those exponents, little n and little m. Little n and little m they are usually small whole numbers like 1, 2, or 3. And they must be determined experimentally as well. Listen, here's a mistake a lot of people make. A lot of people think that N and M are just the stoichiometric coefficients in the chemical equation. Little a and little b, remember those represented the mole ratios, like 1 to 2 moles, etc. These exponents, a to the n times b to the m, n and m are not the stoichiometric coefficients. They are small whole numbers, and they have to be determined experimentally. So K, N, and M all get determined experimentally. Concentration of A, concentration of B, those are just concentrations. You must be able to figure out the unit of K, the rate constant, using some math. We're about to practice all of this. You need to understand conceptually what this rate law means. It means that the rate is tied to the concentration of your reactants. As the concentration goes down over time, the rate of the reaction will slow down over time. All right. Let me talk to you about how you can, one way you can experimentally determine the differential rate law. Remember, there are two rate laws. We're talking about one type today, the differential form. One way of experimentally determining the differential rate law is to use what is known as the method of initial rates. This is where in the lab, different experiments are done where we vary different things. We vary the initial concentrations of the substances that we're reacting, and we see how the rate changes. And from those experiments, we can determine what the rate law is. We can write out a full rate law with the K value and with the N and the M value. So I'm going to walk you through an example. This is a skill that you absolutely must have. So let's look at this example. And remember what our goal is. Our goal is to write an equation, R equals K, concentration of reactant to the N times concentration of reactant to the M. That's what we're trying to write, so keep that in mind. Okay, so here's my reaction. It is aqueous NH4 ions being reacted with aqueous NO2 minus ions to yield, I think that it said water and nitrogen gas. So first let's balance this thing. Let's see. Looks like just by adding a 2 right there, I have it balanced. So I'm trying to write something that looks like this. R equals K times the concentration of NH4 plus raised to the N times the concentration of NO2 minus raised to the M. I'm trying to find K, N, and M. Well, in this experiment, this is the method of initial rates. What we're doing is we are doing 3 different trials with different starting concentrations. That's what that little O down here means. It means initial concentration. Initial concentrations of these 2 substances. So really all I need to do is very carefully compare 2 experiments at a time. For example, experiment 1 compared to experiment 2. What did the experimenters change? What did they actually change? Well, they changed the initial concentration of NO2. It looks like from reaction 1 to reaction 2, they doubled it, didn't they? They went from 0.005 to 0.01. That's a double. So right here, they doubled that variable. And here, they kept that the same. That's perfect, right? In an experiment, we only want to vary one variable at a time. We want to change one variable at a time and see what happens to our independent variable. These are our dependent variables, right? They're our input of our equation. They're what we as the experimenter can change. The rate, the initial rate here, the rate like right when the reaction starts, which they can measure, we're going to measure it in the lab later if we can. The rate right at the beginning is what changes in response to us changing these things. Okay, so here's the idea. We can write a rate law using experiment number 1, compare it mathematically to the rate law for experiment number 2, and we will be able to figure out an exponent. We'll be able to figure out one of these exponents. Let me show you what I mean. So for experiment number 1, I'm just going to flesh this out as much as I can. The rate for experiment 1 is right here, 1.35 times 10 to the negative 7th equals K. I don't know what K is yet. When the rate was that value, I know what the concentration of NH4 was. It was 0.1. So I can plug that in, 0.1 to the power of N. And I know what the initial concentration of NO2 was. It was 0.005 to the power of M. I'm going to flesh that exact same thing out for reaction 2. This time it was 2.7 times 10 to the negative 7th equals K times 0.1 to the N. Remember, they didn't change anything about the ammonia concentration. Times 0.01 this time. That's the new concentration of NO2 raised to the M power. Now, here's what I can do. I can make a ratio between these two rate laws. I can divide them. And when I divide them, I'm going to get some things canceling out. So let's just go ahead and do this. Let's divide 1 by 2. And let's see what I get. Here, I hope that you can see that that's divides out to 0.5 equals k over k, that cancels out. 0.1 to the n divided by 0.1 to the n, that cancels out. Here I have 0.005 to the m divided by 0.01 to the m. So that's going to become 0.5 raised to the m. And guess what? I can figure out what that exponent m now is, can't I? What is it? It's 1, isn't it? So I now know that m equals 1. This is how the method of initial rates works. You perform multiple experiments, you change the initial concentration, see how that affects the rate, write rate laws for those two experiments, and then compare them mathematically, make a ratio, so that you can start to figure out what these experimentally determined exponents are. Here's another simpler way, faster way we could have done that exact same thing. Look, from experiment 1 to 2, I doubled the initial concentration of NO2 minus. I can immediately see that that resulted in a doubling of the rate. This rate is twice this. So look at my rate law. How does the rate of reaction depend on the concentration of NO2? Well, if I double the concentration of NO2, I doubled R, I doubled the rate. So this M right here has got to be 1. It has to be a 1 because there is a direct relationship between NO2 minus and R. I doubled NO2 minus, R got doubled. If I had doubled NO2 minus and R quadrupled, if it increased by a factor of 4, I would know that this M must have been a 2 because the rate would have been proportional to the concentration of NO2 minus squared. But I know that's not the case, right? I double NO2 minus, the rate doubles. That's exactly what I'm saying here. When I compared experiment 1 to experiment 2, experiment 1 has a rate half as big as experiment 2 because experiment 1 had a concentration of NO2 half as big as experiment 2. And so by doing it mathematically, I can see that the exponent on NO2 has to be a 1. I would like for you guys now to pause the video and see if you can figure out what the exponent N has to be. You're going to compare experiment 2 to experiment 3 this time, because in experiment 2 and 3, the NO2 minus stays the same, but the NH4 doubles. So I'll give you a moment to do that. Okay. Hopefully you saw quite quickly that the exponent on NH4 in my rate law has to be a 1 as well. N has also got to equal 1. Why? Two ways we can think about it. From experiment 2 to 3, NO2 stayed the same. It did not change, but I doubled the initial concentration of NH4. What effect did that have on my rate? Well, my rate doubled, didn't it? 2.7 times 2 is 5.4. So doubling NH4 doubled the rate. Those two have a direct relationship. That exponent has got to be 1. If I double this, I doubled the rate, so the exponent must be 1. Here again is how we could do it mathematically. I'm going to compare this time. This is probably easier. I'm going to compare experiment 3 to experiment 2 because experiment 3 has larger values. So when I divide, I want it to end up on top. It doesn't really matter. The rate in experiment 3 was 5.4 times 10 to the negative 7th equals K. I know that my initial concentration of NH4 was 0.2 to the N, and my initial concentration of NO2 was 0.01. And I know that M is 1 right now. I'm going to divide that by experiment 2, where the rate was 2.7 times 10 to the negative 7th equals K. This time the concentration in experiment 2 of NH4 at the beginning was 0.1 to the N. That stayed the same. When I divide these, when I make this ratio, the K cancels out, this cancels out. I'm going to get this divides to 2, this divides to 2 to the power of N. So N, of course, equals 1. Perfect. So now we are very, very close to getting our rate law. And let's think about what part of the rate law do I not yet have? Well, I know what m is, that exponent. I know what n is, that exponent. Now I need to figure out k. Those are the only parts of the rate law I need to figure out. Remember, the rate law is an equation that relates the concentration of reactants to the rate. How does the rate change as the concentration changes? How does the rate depend on the concentration? That's the purpose of the rate law, of the differential rate law. So I've already figured out that the rate doubles when NH4 doubles. The rate doubles when NO2 doubles. So I know that those are both 1. How can I figure out what K is then? This will always be the last step, is to figure out K. First, you're going to figure out your exponents by comparing experiments, writing a ratio, seeing how changing the concentration affects the rate. That will let you find the exponents. That's step 1. Step 2 is to figure out what the K value is. How can I figure out the K value? Well, I know N and M now, and I have all this data where I have the concentrations and I have the rate, so I can just pick one of these experiments, plug all this crap in, and solve for that K value. Does that make sense? So, for example, I can choose experiment 1, and this time it does not matter at all. Just pick one of them, plug all those values in. The rate is 1.35 times 10 to the negative 7th equals K. The initial concentration of NH4 was 0.1. I know I'm raising that to the first power, times the concentration of NO2. Here in experiment number 1, the concentration of NO2 was 0.005. I know that I'm supposed to raise that to the first power. I have one variable, K, and now I can solve for K. And I am getting that K is equal to 2.7 times 10 to the negative 4. All right. Here's where we've got to talk about units. This is hopefully pretty simple math. I know that the unit of R is moles over liters times seconds equals, that's the rate, I'm thinking about the units right now, equals this K value, K, times concentration raised to the first power. Concentration is moles per liter, times concentration raised to the first power. What I'm saying is that K has got to have units such that when it is multiplied by all this other crap, I get this. So let's simplify this. My rate, R, is moles per liters times seconds equals K, whatever the units of K are. And I know that I'm going to have moles times moles, that's moles squared, over liters times liters, that's liters squared. So look, K has to have units such that when I multiply it by this, I get this left over. So you can see that once I multiply by K, I need just 1 mole on the top and 1 liter on the bottom. Right now I have 2 moles on top, mole squared. I have 2 liters on the bottom, liters squared. So what does K, what must K be? K has got to cancel out one of those. So I know that K must be liters per mole, so that whenever I multiply this, I only end up with 1 mole per 1 liter. What else does K need to give me? K needs to give me seconds on the bottom, so I know that I need seconds right here on the bottom. So that has got to be the unit for K, liters per moles times seconds. Let's talk about different ways we could write this. Liters per mole, what does that remind you of? It reminds you of molarity. Molarity is moles per liter. This is just flipped. So another way of writing that would be big M is molarity to the negative first, that means flip it, times seconds to the negative first. That is the unit for K in this case. So that's another way that we could have written K. All right. If that does not make sense to you, if you're not used to this math with units, it works the exact same way as regular math. You just kind of have to work backwards to figure out what K is. You can even solve for K like a variable right here. Multiply both sides by liters squared, divide both sides by moles squared. You'll be able to figure out what K is. You can use this just like algebra to figure out the units for K, but finding out the units of K will be very, very important. So what I can do now is actually write my final rate law. The final rate law for this equation is R equals K, which was 2.7 times 10 to the negative fourth, times the concentration of NH4 plus raised to the first power, times the concentration of NO2 minus raised to the first power. And that is the rate law for this chemical reaction. Remember, step one is always going to be finding out what those exponents are by looking at the experiments. I saw that NO2 doubled, the rate doubled, that has got to be a 1. I saw that NH4 doubled, the rate doubled, that has also got to be a 1. Then to solve for K, which will be the last thing you do, you just pick an experiment, plug the values in, and solve algebraically for K. You have got to think about the units for K. We know that rate is going to be in moles per liters times seconds, so K has to have units that will get us there. If this is moles per liter times moles per liter, then K has to have units of liters per mole seconds, just like that. Okay, we need to talk about some terminology. Let's look at a very simple example of a differential rate law. Let's say we just have one reactant, reactant A. Let's say that we solve experimentally and find that N is equal to 1. Remember that N is determined experimentally and must always be a small whole number. Earlier we found that for both of our reactants it was 1 and 1. Let's say that N is 1. We refer to a reaction with an exponent of 1 like this as a first order reaction. You must know that term. That means that if we double that substance, the rate gets doubled. That's exactly what we saw in our previous experiment. What if N ends up being a 2? We call it a second order reaction. That means that if we double this, the rate gets affected by the square of that. So if we were to double A, the rate would get quadrupled. If we were to triple A, 3 squared would be 9. The rate would get multiplied by 9. Does that make sense? Another possibility is that you find that the N is 0, which means that anything raised to the 0 power is 1. This equation would just simplify into R equals K. That means that the rate does not depend on the concentration of A at all, and that is possible. So first order, second order, or 0th order reactions will be the important ones for you to be able to think through. What if your chemical reaction has 2 reactants, like in the example we just got done looking at? What language do you use? Well, in the last example, we had a 1 here and a 1 here. So we have 3 ways of talking about it. We could say that it is a first order reaction with respect to this reactant. In other words, the exponent on reactant A is 1. We could say it's first order, this was 1, with respect to the second reactant. Or we could say that overall, it is a second order reaction. So the overall order of the reaction, first, second, whatever, is going to be equal to N plus M. So the whole reaction overall, I would say, is second order. In the example that we just got done working, it was a second order reaction overall, first order with respect to NH4, first order with respect to NO2 minus. If N had been a 2 and M had been a 1 or something, it would have been second order with respect to A, first order with respect to B, third order overall, for example. That's just some important terminology that you have to get down. Okay, last thing for today. I mentioned several times that it is important for you to discuss the rate of a reaction from the perspective of a certain chemical, from the perspective of the reactants or the products or a certain reactant or a certain product. Remember back here when we first started talking about this, we noticed that the production of NO was twice that of O2. The rate of change for NO from NO's perspective was double the rate of change of O2's perspective because NO had a coefficient of 2 and O2 only had a coefficient of 1. For every 2 moles of NO, we only made half as much O2. So it makes sense that that O2 had half the rate. So sometimes you have to be able to move fluidly from one rate to another, and that's what these little equations here help you do. Remember that this piece of terminology right here is the rate of reaction, the rate of change from the perspective of with respect to that particular substance. So if you need to go from one substance to another, you can just write a little equation, and it's going to be just like this. I'm using negative signs for the reactants because their rates will be negative. Their rates will be going down. They'll be decreasing. Typically, we're only worried about the absolute value of the rate. Typically, we're worried about the size of the rate, the speed. But it is important for you to understand that the rates of the reactants are typically technically negative because their concentrations are decreasing as time goes on. Their slopes are negative, whereas the products, C and D, are positive. So to relate rates, to shift your perspective from one chemical to another, all you have to do is just set the rates equal to each other and then put 1 over the stoichiometric coefficient. 1 over little a times the rate of A is going to equal 1 over little b times the rate of B. So here's an example of all of this. This is a little bit of a complicated, confusing slide, but let's take it piece by piece. We have to remember, we always define a rate with respect to a specific chemical. So if we define the rate in terms of what NO2 is doing, we would write our rate law like this. The rate is being defined as the rate of change of NO2, and here's the rate law for that. Boom, right there. That's the differential rate law. That should look familiar. We could experimentally determine what that little n is, what that exponent n is. But if we define the rate in terms of O2 production instead, we would have a different rate law. That's what this little apostrophe, we call that prime right there. That's what it's doing. It's saying, hey, this is a different rate law. We've shifted our perspective. Now we're looking at the rate of change of O2. And you need to know that everything about it is going to be the same, but it's going to have a different K value. So I'm going to call this K prime. Here's why. Here's how this works. We've already kind of thought through this. The rates are related to each other in this way. One half the rate of the NO2 consumption is equal to the rate of O2 production. In other words, the rate of O2 production is half as large as the rate of NO2 consumption. Notice that just comes from the chemical equation up here. It comes from this idea here. If I'm comparing, for example, C and A, those two rates, here's what I would write for A. 1 over its coefficient is equal to the rate of C times 1 over its coefficient. That's exactly what I did right here. NO2 has a coefficient of 2. So 1 over 2 is 1/2 the rate of NO2 consumption is going to equal the rate of O2 production. So the rate of O2 production is half as big. It is 1/2 of the rate of NO2 consumption. That's exactly what we saw in that graph earlier. All right. Why is this the case? Once again, because for every 2 moles or for every 2 molecules of NO2 I'm consuming, only 1 molecule or 1 mole of O2 is produced. So of course the rate of O2 production will be half as big as the rate of NO2 consumption. It's really that simple. How is this related to the rate law itself? Well, because for every 2 NO2 molecules that are consumed, only 1 O2 molecule is produced, then I know that the rate of NO2 consumption has got to be twice the rate of O2 production. That's just this exact same thing, just rearranged a little bit. 1/2 the rate of NO2 consumption is the rate of O2 production. That's another way of saying that is the rate of NO2 consumption, bring this to the other side, is twice the rate of O2 production. NO2 is consumed at twice the rate at which O2 is produced. So I know that the rate with respect to NO2 is twice the rate with respect to O2. So I'm able to say this, and therefore I'm able to say this, that my K value here, if I am defining my rate with respect to NO2 consumption, this K value is going to be twice as big as the K value down here. All right. That is just another way of saying all of this. So how you define which reactant or product you are analyzing, it could affect your K value. So the value of K depends on how the rate is defined. If this is confusing to you, I understand. I really wouldn't worry too much about this. What I am more concerned with is that you guys get the main ideas of what a rate law is, what it does, that you understand this, that you understand how we can use the method of initial rates to find the exponents and then find the K value, that you understand how to find the unit of K, and that you understand what this means, that the rate depends on the concentration. If N is 1, we double the concentration of A, the rate gets doubled. If N is 2, we double the concentration of A, the rate quadruples, etc., etc. And I need you to understand the language of orders of reaction. If N is 1 for the reactant, then the rate with respect to that reactant is first order. And then we can talk about the overall order of the reaction by adding these exponents. If these are both 1, like in our example, the overall order of the reaction would be 2, etc., etc.